Morning, physicsy people. We're going to go ahead and do some practice problems for us. The plan really is Quiz Friday, right? So you should be doing this on Thursday, Quiz Friday. The Friday's quiz will be more like the simple harmonic motion quiz, like a class quiz, but smaller unit, so it'll be shorter quiz and that kind of stuff. But if we're having trouble with these problems, swing into the Google Meet and we can work a few of them together. But I'll go ahead and run through these so you have an answer key and that kind of stuff. But do the problems first, then do this. Don't just watch me do the problems, right? So in an experiment, measuring the speed of sound, a gun was shot 715 meters away from an observer. It was heard 2.13 seconds after the flash. What was the speed of sound in air at this time? So, that's speed. So we can just do like a velocity equation. That's just distance over time. We can assume that the flash got there basically instantly, right? Because the amount of time light is going to take to get there is very, very tiny. So if we use 715 meters divided by 2.13 seconds, right? 715 divided by 2.13, that's going to give us 335 meters per second, which makes sense because air is supposed to be around 340, right? But it's going to change based on humidity and density, little bits. Okay, sound travels at a speed of 1513. I can't speak. 1530 meters per second in seawater. A signal sent down from a ship is reflected at the bottom of the ocean and returns 1.35 seconds later. Assuming the speed of sound was not affected by the change in the water, how deep was the ocean at that point? So that's basically the same equation, but we're going to do velocity times time equals distance. But I'm going to cut this time in half because that's the time it took to go down and back, right? So I'll do 1530 meters per second times 1.35 over 2. So 1530 times 1.35 divided by 2 will give us 267 meters down. Oh, yeah, no, that's not right. I was like, that seems way too little. I missed the 1 on that. 1530 times 1.35 divided by 2 gives us 1,032 meters. That makes more sense, right? Yeah, so that's pretty straightforward. A train, we are all kinds of fuzzy again. A train at rest blows a whistle to alert passengers about to depart from the subway station. The pitch of the whistle is 1.14 hertz. The speed of the sound in air in the subway tunnel is 342 meters per second. The speed of sound is this. What is the wavelength of the sound in air? So let's see. We've got the speed here, and we've got the frequency here. So if we go, let's see, speed equals frequency times wavelength. Whoops, I did the new thing, right? So we know what the speed is, which is 342 meters per second. Divide that by 1.14 per second, 1.14 times 10 to the fourth per second. So 342 divided by 1.14 times 10 to the fourth gives us 0.03 meters or 30 centimeters. Either of those would be just fine. Right, so 0.03 meters is what we're talking about there. What is the distance between consecutive areas of compression and refraction in a spherical sound wave spreading out from the whistle in the air? So they're basically saying the whistle makes a noise. What's going to be the distance between those waves, the distance between the consecutive areas of compression and refraction? So they're saying, what's the wavelength in these spherical waves? They're just doing that in a weird way. So 0.03 meters. Assuming the sound is loud enough to be heard from the end of the tunnel, which is 1,200 meters long, when it was heard through the air. When was it heard through the air and through the rails? Well, it's going to travel faster through the rails. So again, we're at velocity equals distance over time. So if we do distance, which is 1,200 meters, divided by 1530, no, that was a different number. That was in water. 5130. So in iron, 1,200 meters. Oh, I need to adjust this so you can see where I'm writing. 1,200 meters divided by 1530, that's the meters per second for iron. So 1,200 divided by 5130 is going to give us 0.23 seconds after the whistle blows. It's going to be heard through the iron. And through the air, we would do the same thing, 1,200 meters divided by 342. And that gives us 3.5 seconds. Right. What is the apparent frequency of the sound waves that have reached the end of the tunnel? Oh. Okay, I think we've got the, whatchamacallit, the focus back in play here. So, sorry, what is the apparent frequency of the sound waves that reach the end of the tunnel? So if the train's moving, right, towards the end of the tunnel, that's going to compress those together. If it's moving away, it's going to stretch those out. So if we go back to the beginning, a train at rest blows away. Well, the train's at rest, so it's going to be the same. What's the apparent frequency? The frequency is the pitch. So 1.14 times 10 to the fourth per second, right, would be the apparent frequency there. Yeah, so they acted like that's tough, but that's actually not a very hard question at all. As the train left the station, so now it's starting to move. Did the frequency appear to change for the listener on the platform? Yes. Inside the train? No. At the other end of the tunnel? Yes, right? For the listener at the platform, those waves are going to get closer together, so the pitch is going to go up. Here, you're inside the train, so you're moving with the train, so your relative speeds don't differ, right? So that's going to be no change. And here they're moving away from you, so they're going to get further apart, and so there the pitch is going to drop. All right. All right, so let's flip it over and look at the backside. There we go. While practicing an instrument at home, a young drummer produces a sound of 0.5 watts of power. Assume that the sound wave spreads spherically with no absorption in the medium. What is the intensity of the sound waves that reach the walls 2 and 4 meters away? So this is that equation there where we do power over 4 pi r squared, where r is the distance away. So it's that inverse square law thing, and that's going to be our intensity. I can't even think off the top of my head of what the variable for intensity is. I'll have to look at that, right? So anyway, 0.5 watts divided by 4 divided by pi divided by 2 squared. 4 meters away, it is 0.00995 watts per meter squared. And let's see, at 4, it's going to be 0.5 divided by 4 divided by 3.14 divided by 4 squared. It will then be a fourth of that, 0.0024 watts per meter squared, right? It's going to be a fourth because you're twice as far away, so 1 over 2 squared. This is a fourth of this kind of thing, right? What is the intensity of the wave as it reaches the family room 8 and 12 meters away? So again, 0.5 divided by 4 divided by 3.14 divided by 8 squared. So now we are at 6.2 times 10 to the negative fourth for the 8. And the 12 would be 0.5 divided by 3.14 divided by 4 divided by 12 squared. Now it's going to be getting significantly less. 2.76 times 10 to the negative fourth watts per meter cubed. Was the intensity and approximate decibel level at the neighbor's house 50 meters away? So 0.5 divided by 4 and pi and 50 squared. So that is 1.59 times 10 to the negative fifth watts per meter squared. And so if we look up 10 to the negative fifth is about 70 decibels. The sound level, let's see, sound level 5 meters away from a jackhammer, that is exactly 100 decibels. So we're 5 meters away, it's 100 decibels. So 100 decibels, the intensity is 0.001. So 0.001, whoops, got an extra 0 there, 0.01 times 4 times pi times 5 squared will get us our power. Basically, just multiply all these by the intensity, right? So 4 pi r squared. And so 0.01 times 4 times 3.14 times 5 meters away squared. And that intensity is pi. Does that work out? That's weird. Okay, so that is 3.14 watts. What is the, that's down here. I was ahead of myself. I knew where they were going. 0.01 watts per meter cubed, right? They're just matching up right here. What is the distance from the jackhammer? The noise intensity will be 10 to the negative 8th. So there, if we just do the 3.14 divided by 4 pi r squared equals 1.0 times 10 to the negative 8th. So 3.14 divided by pi divided by 4 and divided by 1 times 10 to the negative 8th. And now that I need to square root. And so it's going to be 5,000 meters away. So 5 kilometers away before it gets down to a pretty quiet volume. Right? Hopefully that helped. We've got to do the 411 problems. We're not going to I'm not going to work those together. I think we just worked enough like that, but we can pop the answers on there for you. So you can double check your answers, right? There's those guys. And if you're not getting any of those answers, you can't figure it out, just come to the Google Meet and we can work those together. But we should be able to work all these kinds of problems. A few conceptual ones about Doppler effect and changing pitches, the idea on the Rubens tube a little bit there, pitch versus frequency, and then just the kinds of problems we were just working the last couple of days. That quiz will be over on Friday.